We are live. Hello, everybody in the room so far. Welcome, welcome. We have an amazing workshop. We got another technical workshop for you. But just as we wait for some folks to continue to join us before we kick off at 6 o'clock, I guess that's 6 o'clock my time. I'm not sure where you guys are in the world, but let me know in the chat. Let me know what time it is where you're at, where you're tuning in from. But I'd like to welcome Bitcoin Bay's very own Jerry Qian to the stage. He's gonna go sight unseen. He doesn't have a camera where he's at, so yeah, we're gonna talk to this lovely digitized avatar that he's got going on. And just as we wait for some folks to join us, I want to get to know Jerry a little bit better. So I personally have known Jerry for a while, and I was surprised to learn recently that he has a degree in biology and ecology. So I'm of the belief that blockchain is going to affect and touch every industry, every area of study. So I'm interested to hear Jerry's thoughts on how biology and ecology are going to be affected or used or integrated with blockchain technology. What do you think, Jerry?
Yeah, thanks, Jordan, and thanks for the intro. I gotta say, to be honest, the biology aspect was really before I discovered Bitcoin. So definitely, had I learned about Bitcoin while I was in university, I would definitely pivot towards that a lot more. But overall, it really gives me a very holistic sense, seeing like the big picture of things and where things could actually fall together. So it's very, very kind of like general, jack of all trades, but being able to actually piece together, like the super technical stuff that, very few people actually understand. But once you boil it down to simpler terms, how do you actually build something new and create it out of it? So I think it's really just like making a different train of thoughts, or like training your brain to think differently about these kinds of problems.
Very interesting. Super cool. So I know you also you're an advisor for existing businesses that want to integrate blockchain technology into their business. So what is your approach when a new business approaches you for your advisory skills, and what kind of advice do you have for our hackathon participants that are looking to build new businesses in the blockchain space?
Yeah, so for a lot of these companies, it really is boiling down to, do these companies really understand the idea that they're trying to attempt, right? The endeavor. It's good to know like the high level, very overall like vision of the project, but a lot of times when you dive deep into the details, you know what they say, right? The devil's always in the details. So for a lot of these things, like for example, we've touched with people who wanted to do medical records, land registries, blah blah blah, right? And sometimes these kind of details aren't even very highly technical. Sometimes it's just a matter of how exactly are the end users going to be interacting with the system, right? So a lot of times it's just really on getting the people to understand that not just like the interface, not just technology, it's like a very, very holistic, like different approach to how you actually tackle these problems. And so we really just try to work with them from the grounds up to build like that solid foundation so that they're not like halfway up like a skyscraper and then realize there's no foundation at the bottom. Like everything is just going to crumble afterwards. So that's where we really try to deliver value for. And so, like what I would really say to everyone participating is really just try to maybe not like dedicate all of your energy into looking into like the technical or like those kinds of stuff, but try to like spend a little bit of time just understanding those portions well enough so that you can explain it to others.
That's some amazing advice. While you're talking, I recalled like in the early days of the internet, like every kind of business was trying to find their way in there, and I think the very common joke was like adopt a pet. The idea of adopting a pet on the internet was this bizarre idea that obviously didn't really work out. So have you ever been approached by, and that also begs the question, like blockchain isn't for every single use case. So have you ever been approached by like a bizarre adopt a pet blockchain kind of idea?
We've actually been approached for various different ideas that, especially during the ICO days in 2017. Honestly, it was just any random idea plus blockchain plus ICO tokens, right? So I won't bore you guys into too much details, but let's just say there are some ideas where it literally has nothing to do with blockchain, anything like that. It's just taking the buzzwords and it's like, oh, okay, let's just use it in a completely different context.
Right.
So yeah. I mean, one example that we've gone through was someone was actually trying to sequence genes and sequence DNA, but doing so like how these kinds of blockchain networks distribute the data. So it was very, very interesting, let's just say, that idea. But
Yeah,
I don't
it
know how
sounds
viable it actually could be.
right. It does sound super interesting. I'd like to know a little bit more about that. But in any case, I think we're going to jump into your workshop in just a sec. I see a bunch of folks have joined us now. So we're going to start in earnest. But before I do, I want to draw everybody's attention down below the screen here and check out the Ask a Question button. Jerry wants you guys to be like interactive, and he wants you to speak up if you have any questions while we're going through the workshop. So if you have any questions, by all means, drop it in there. And if your question is like very technical and difficult to convey by just typing it out, we are going to open it up for people to actually come on the stream with us live, and we can have a discussion, and you can ask your question using your voice chat. If you want to come on camera, by all means, you'll be able to do that. So if you want to do that, please just mention in the chat, I'd like to come on screen. You can use an emoji, like put a hand up kind of emoji. I'm going to be here the entire time monitoring the chat and the ask a question. So either way, we can get your question injected into the stream, and Jerry can answer those questions. Also, take a look just beside the ask a question button there. There's a poll, and I see some folks have already been starting to answer it. So I asked, do you come from the business side or the technical side of the industry? And we've got about a 50-50 split. So that's pretty encouraging. We definitely want to be building businesses in this space, and that requires some business acumen, not just technical acumen. So that's great to see a good split there. Another question I have here is, are you familiar with Ethereum development? A ton of folks are saying yes. One person is saying no. That's cool. That's super cool. And another question we have here is, are you familiar with BCH development? So a lot less people are familiar with BCH development, but everybody wants to learn. So that's very encouraging. So you've come to the right place. You're in great hands. Jerry's about to take you through an awesome technical workshop where you're going to learn a ton. And again, if you have any questions as we're going through, please put up a hand, mention in the chat if you want to come on screen, or you can go ahead and use the Ask a Question button. All right, so I'd like everybody to welcome to the stage Jerry Chen. He's been involved with Bitcoin and blockchain since 2013, so he's another one of the OGs in the space. He's an advisor to technology companies looking to integrate blockchain technology, and he's a founding member of Bitcoin Bay. So I'd like everyone to give a nice digital round of applause for our very own Jerry Qian.
Hey,
Welcome,
thank you
Jerry.
so much. Thank you, Jordan. So yeah, thank you everyone for just answering the quick poll at the beginning. I wanted to ask this because I want to get a sense of what the audience is kind of like. So if anyone else is like joining in afterwards, definitely hope that they'll also fill in this poll so we get a sense. So yeah, I wanted to go through today the kind of like the basics of Bitcoin Cash app development. It's a very interesting technology to look at, especially when you have an Ethereum background or just familiar with it. In that it has obviously it has advantages and disadvantages, where you may pick one chain over the other for doing certain things, but not the other. So let's just jump right into it. So before really getting into like super technical content, I guess like this is already kind of technical, but let's just review how exactly these wallets work. So most people are familiar with the the 12 words or the mnemonic words for recurring your addresses and your key pairs. So I won't go into too much detail into it, but just know that current days in basically every single wallet, there is a derivation strategy for creating all of the addresses that you will need. This way, you can make all of these wallets actually compatible with each other. So imagine if one wallet doesn't actually follow these kinds of derivation strategies, what will happen is that a user who had money in one wallet would all of a sudden see zero balance or an empty wallet if they move to a wallet with a different derivation strategy. So even though the funds are still there, it's a matter of how do you actually communicate that fact to your end users. So this is the starting stage of it. As I mentioned, most of the wallets nowadays are using this derivation strategy called BIP44. I believe the only exception or the only notable exception right now is Monero, but that's because they have their own methods of making all these addresses. So just to go quickly, people know that there's like the 12 words, but you can actually go up to 24 words. So in this chart right here, you can see the number of words highlighted in this red box here. And there's a whole bunch of entropy values. So you can see that 128 corresponds to 12 and 256 corresponds to 24. So these are just numbers that just correspond to like the byte storage, and that's how you basically get these kinds of stuff. So for some of the wallets, they'll actually have the option for you to toggle how many words you want to use. Some of them, unfortunately, they don't. So again, it's a matter of like how do you actually make these wallets super compatible with each other. So this is something if you guys are looking to build these kinds of wallets or some sort of wallet feature, this is something you guys could consider. So let's just go to what exactly this BIP44 derivation strategy is doing. So for people who have various different cryptocurrencies on their wallets, especially for multi-coin wallets, what they'll notice is that the derivation path for all of these different coins actually just changed by one value, which is labeled the coin type right here. So there's actually an entire list of these different coins that are registered. And essentially, if you create a new blockchain or anything like that, you can go onto this GitHub link at the bottom and essentially just request that your coin be registered with this table right here. So this is essentially what all the developers are referring to when they're setting all of the wallet values. So for example, with Ethereum, if you were to build a wallet that's Bitcoin and Ethereum compatible, you would need to specify the coin index of 60 and 0 for all that. So this is one way of essentially building out the multi-coin wallet for all of these coins that you do want to support. That doesn't say that is sufficient to do so, but it's a first step. So there's a few more values in this BIP44 strategy. So after the coin type, after we know which cryptocurrency we're dealing with, there's 3 more values here. Now in Ethereum, what happens is that they actually, I believe some of the wallets in early on, they modify this so that after the account, you only have an address index. This, if anyone played with MetaMask, this is equivalent to creating a new account. So anytime you want to create a new account with the address and all that stuff, essentially you're just increasing this address index. But you can see that there's a lot more numbers here that you can actually change. And for some of the wallets, they'll actually toggle the account value here. So some of the wallets, they could make it so that you can create let's say a checkings wallet or like a spending wallet. And then you can create like a savings wallet, right? So different accounts, they can track different funds for different purposes. And so this is like, again, another value for people to basically use to help track all of these addresses. Just touching briefly on these wallets. These wallets also support something called extended public keys or extended private keys. And the whole idea is that if you want to share your addresses with someone, but not the public and private key pair, you want people to basically be able to generate all of the public keys on demand. So something like this xpub extended public key down below would essentially translate to all of the different public keys, public key addresses that is available to this key set, or essentially the derivation path. One thing to note is that obviously, public parent keys cannot be generating private child keys. Actually, public keys can't be generating private keys at all because that doesn't make too much sense. But you can definitely see the different combinations of use cases where, let's say, I have a merchant app, and because I have a lot of people on the staff team, I don't want to be giving out all of the key pairs to all of the employees. So what I'll do is give out the extended public key so that the staff can generate all of the receiving addresses, but only the store manager or the restaurant manager will be able to control the actual sending of the funds from out there. So that's a few of the cool ways that you could actually look at how do you present these addresses to the end users. Now, that's a fairly quick overview of the wallet and address generations. Again, guys, feel free to type your messages in the chat or raise your hand if you want any clarifications on that. This talk will be fairly technical, so I'll try to explain it as best I can. So moving on to, okay, so now you have these wallets and all of this stuff, but how do you actually present it to an end user, right? So this is a very general blockchain application architecture. This can work for platforms like Ethereum, but in this case, we're going to use Bitcoin Cash. Essentially, all of this is still very same. It's just swapping out the actual protocols that you're dealing with. So on top here, we can see is the front-end interface, which is what your end users are actually seeing. And their only interactions are through these remote protocol calls interfaces or directly communicating to the backend servers of your applications. Because Bitcoin Cash does not have a virtual machine, you can't directly just send the information to the blockchain node. All of the information that you're sending to the Bitcoin Cash blockchain is basically going to be sent in raw hexadecimal bytes. So all of the processing, all of the other stuff will basically have to be done through these kinds of intermediary servers and RPC call interfaces. So let's go there. So the other big difference between Ethereum and Bitcoin or Bitcoin-related derived protocols is the idea of UTXOs or unspent transaction outputs. Now, in Bitcoin, the unspent transaction outputs are actually used to help verify that the coins actually came from a mined block. In other words, you're not just creating these coins out of thin air. It actually had to come from some sort of a Coinbase that these mining farms, put in work for. So one major benefit to this is that if you were to be tracking just one transaction or like the one address, you could basically trace all of those actions back to where they're from without having to validate the entire transaction set of what that block consists of. So let's take a look at this image right here, right? If I were to say I want to track output 0 in transaction 6, you can see that there's a series of transactions and chains and whatnot that we have to go through before we get to the output 1 in transaction 0. Now, I didn't need to look into the transaction 1 or the transaction 3 where those UTXOs or like those traces didn't really affect me, right? All I needed to do was validate that my UTXO actually is valid and is part of all of these transaction chains that's recorded on blockchain. So you guys can see sometimes there are two outputs, sometimes there's two inputs. You can actually have many different combinations of which. I do have to double check what the actual limits for all the inputs and the outputs are, but I know you can have at least 10 different outputs. So there's a lot of different ways to actually be paying out people and to be combining these payments in. So
I got a quick question, Jerry.
Yep.
So say you have an output there of 50K, but you only want to send like 30K to someone. How does that work?
Yeah. So sending 30K, if you only want to send 30K, what happens is you'll basically be breaking up. So let's take an example right here from the very, very beginning on this diagram, the 100,000 Satoshis. So that's the original amount. And so in transaction 0, we're actually breaking up this 100,000 into 40,000 for the first input and 50,000 for the second input. Now you'll notice that the 40 plus the 50, that doesn't add up to the 100,000, right? So what the Bitcoin protocol actually does is that the difference in the inputs and the outputs would actually amount to the transaction fees, right? So when you're doing all the splitting up, you got to make sure that you're splitting up the correct amount, meaning that it has to be less than the input, and that any remainder that you're not splitting to, you have to keep in mind that that is automatically going to be sent to the mining fees for all the miners. Actually, early on, I believe there was one person, I think it was in 2013 or 2012 or something like that. They actually sent out 10,000 Bitcoins worth of transaction fees because they were constructing these transactions incorrectly. So just something to keep in mind.
So does that mean then, is it possible then to send the remainder or a certain portion back to yourself so that you're not doing that?
Yes. So essentially, if we see here in the transaction 0, we can imagine that let's say output 0 is sending it to someone that we want to send the money to, and then output 1 would be sending us returning the change back, right? So the remainder of what is not sent to this person will be sent back to our own address. So let's say this transaction, the second transaction is also under our control. That's basically how you would do it. You would specify who you're sending it to, and then you would specify where you want the remainder amount to go back to.
That's super cool.
Does that clarify it?
Yeah, super cool.
Awesome. So just a few rules, of course, to all these transactions. So we went through the multiple inputs and outputs. We went through all this stuff. One thing, again, to keep in mind, the values of the inputs has to be greater than the outputs. Can't specify that enough. If you do try to spend an output that's actually greater, you're immediately going to get error messages. And the last point, I guess, is that all these transactions are actually going to be broadcasted as hexadecimal bytes. It's due to saving up space and also for increasing the efficiency of things. So let's just take a look at what an actual transaction will look like. At the bottom here, you can see a whole bunch of numbers and letters, which are actually in hexadecimal. And this is the raw transaction representation of the actual inputs and outputs and all of the locking scripts. So we can see here there's a few important areas to highlight for this UTXO. First, we have the transaction ID, actually where this transaction came from, and the kind of details for that address. Then we can see the actual inputs and outputs here. So we can see there's one input, I believe, with this locking mechanism. And then here in the output, we're actually going to be specifying two output values. First one is going to be sending this much like a whole bunch of Satoshis to the destination. And then the second one is actually going to be sending out 0. And we're actually going to come to that very shortly. So just to clarify or like better explain like the key components of it, the transaction ID is what you'll get when you broadcast the transaction that you want. And if it is valid, this is what will be included in the blockchain with the Merkle trees and all that stuff. So if you go to a block explorer, just copy the transaction ID, hopefully you actually see all that information out there. The output index here is fairly important to track. If you guys recall, there could be multiple different inputs and outputs. So the V out will actually be tracking the output index, and then there will actually be one that says V in to track the input index. So here, this UTXO is part of this transaction ID, and it says the output index is actually 0, or the first one. And the locking script to basically protect the keys to make sure that the funds are actually in the address is through the SIG pub key right here. So you can see there's a whole bunch of values, which I basically just translate into what they are. And if you can see, there's a 14 right here. This 14 is actually not the decimal 14, not what we think as 14. This is actually hexadecimal 14. And I believe this will translate to 20 in actual decimal format. So 20 is actually the length of public key hashes for many of the transactions that we make. And we'll go into how that works a little bit on. But yeah, essentially the purpose of this is to get you guys comfortable with all these byte values and how they correspond with opcode commands that you can then use to construct your transactions with. Moving on. So just briefly, I know we didn't really ask this in the polls, and this is where I guess it's fine.
We can totally add a poll right now.
Yeah, what Bitcoin does with the transaction and the operators with the opcode is that it uses something called a script operation or a script stack. And what this is essentially like a stack operation where the values are popped in, and what you're trying to get out at the very end is a value of true or 1 to indicate a valid transaction, a valid Bitcoin transaction. So we have here a very, very simple example of how like a stack would look like. So here is, obviously just a very simple addition equation. 1 plus 2 is equal to 3. And so what happens here is that the values op1 and op2 are dropped in, and then we're dropping in the op-add. Now, the op-add is actually a function which will take the 2 stack items below it, and it will try to combine it together. So afterwards, we'll pop on the op3 because that's what it says, and then we'll pop up the final operator, which is op equal. So if you go through all this process, you'll essentially see that the op-add will convert the op2 and the op1 and turn it into basically op3, which is the value of 3. And then, of course, op equal will say, well, op3 equals op3, therefore, it will return an op true. So again, if we get an op true, or essentially is 1, that means that the stack is good to go ahead. This Bitcoin transaction will be marked out as valid.
Quick question there. So these opcodes that you just used, those are like, for example, and we're gonna look at more specific opcodes and how they might be actually added together to produce an output.
Yeah. So right here in the very next slide, what we actually see is the most standard transaction script for basically every single wallet for most of the exchanges. It's called pay to pub key hash. And what this is doing is essentially it's storing a hash of your public key. so that there's nothing visible on the blockchain that will say, this will tie to your address or your signatures, public keys. And what this actually does, if we go through the stack operation right here, so the script pub key again is the locking mechanism. The script sig is basically the key that we're providing in. It has the signature for the private key and the public key values. So what happens is the script sig, the signature and the public key, will be placed to the very, very front. And then we're going to add on the script pub key, which is all of this stuff afterwards. So because the sig and the pub keys are just values, just like op1, op2, those kinds of stuff, they'll just be popped into the stack with no operations to be done. The second step would be to duplicate op-dupe, which is to duplicate the topmost stack item. And so in the next line, you'll see that there's 2 pub keys right here. So if we just continue all this process, the next one, hash 160, which is going to create a hash of this pub key value. And then we're going to provide the public key, the pub key hash that was stored in this transaction when it was first made. So once these 2 hashes are here, we can then check if they're equal. And if they are, we're actually going to use a special version of equal called equal verify, which instead of returning true, a stack item true, it would just simply get rid of these 2 items and proceed to the next step. If this step is false for equal verify, then the entire stack operation will just stop right there. And then some error message should come out and say, hey, something's not matching up or something like that. So assuming that the pub key hashes are actually matching up, these 2 values go away through the verify operator. And then we're just left with a signature and the public key. So the op check sig will return true if it's if it matches, and false if it's not. So that's basically the step-by-step operation for how these transactions are actually secured and locked into place. And how we can know that if you have this address, it will have this balance out here because of this signature and pub key unlocking mechanism. Hopefully I'm not going too fast for you guys. Here we have a few examples of other more popular or more popularly used script pub keys or the locks. So again, the first one is the pay to pub key hash or P2PKH. The second one is what you commonly see early on anyways, is something called pay to pub key. And you can immediately see how it's very, very similar to the pub key has P2PKH, except the pub key is actually stored on the blockchain in the transaction itself. So in case like the algorithm SHA-256 or whatnot gets broken by quantum computing in the future, this storage method, number 2, would not be very safe because people would just go on the blockchain, take a look at what's actually being written, and they'll see, oh, here's a pub key. Well, let's just crack it because I have this quantum computer now, right? So if you have a hash of the pub key, it just adds on an extra layer of protection so that it's not easily crackable.
Quick question there, Jerry. Was that something that is recent, or has that been in?
Yeah, this is a very this is basically predates the pay to public key hash. So you can actually see in the in some of the very, very first transactions, this will be like one of the formats that they'll actually send it to. I won't go into like how old transactions really went about, but this is one of the more popular formats before the pub key hash method was created.
Right. So at some point we're like, oh no, quantum computing's coming. We got to start protecting ourselves. So this is one of the safeguards.
Yeah, and I believe, so this is the next slide right here. So the number 1 here, this is actually a little bit outdated. This data was compiled in 2015, And back then, like everyone was just using wallets. So the number one script pub key that you see here is the pay to public key hash. And the reason why is because every single wallet basically integrates that. But you can see the next highest occurrence, at the very least in 2015 or 2014 or so, is something like op data check sig. So this one, number 2 and number 4, are actually just the regular pay to pub key, right? So you can actually see that there were quite a bit of occurrence of this format. But again, it's just a matter of how secure is it? Do you really want the public key to be on the blockchain when you can just masquerade it with this hashing format, right?
That's super cool.
Does that clarify it?
Yeah, that's cool.
Yeah. Okay, cool. So yeah, I'll just jump into what these last two are doing. So number 3 is something called multi-sig, or multiple signature. And it does exactly like it sounds, right? What you have here is a transaction setup where the unlocking mechanism actually has 3 possible public key pairs that you can actually do the unlocking with, but you only require 2 out of the 3 that you actually set there. So I believe in Bitcoin Cash right now, there's a limit of, I think it was like 16 public keys that you can actually put in here for the check multi-sig. But yeah, essentially it's just going through the process of, hey, this sig here, sig number 2, does it match with pub key 1? No. Does it match with pub key 2? Yes. And then we go to sig 3, and it just repeats that process. And when we hit the 2 here out of 3, then this check multi-sig will evaluate that everything is normal, will return a true, and so therefore approving the transaction. I highlighted this op1 in bold here because unfortunately in Bitcoin at the very least, and Bitcoin Cash is a fork of Bitcoin, so this is carry legacy work. But the multi-sig operators actually will pop off an extra stack item, which means that if you did not have this op1 here, it'll actually be expecting another item and say, well, I don't see another value here. This operator must return false then. So a workaround actually is just to put in any value you want. Typically, people will put in op1 or op2. I don't know if op0 will work, but essentially, all you really need is just like an extra item in this key, script sig key here. And once you have that extra dummy item, you could get this going. There have been talk about utilizing this, but I guess it hasn't really been implemented into nodes as of yet. So yeah. So the last one here is pay to script hash. And this is actually really interesting in that I believe this was activated through a fork, a soft fork or a hard fork. But essentially what's going on is that it's actually creating a secondary stack, or like a heap, where it tracks all of the redeemed script. And so what's going on here is that on the blockchain, what people will see is this op hash 160, and then a hash, a really long hash, and then it just says op equal. And so in order to actually validate this, the first step would be to take this entire redeem script that you're putting in as a key and combining it into one value so that you can do the hash operator. So essentially, it will be making a copy of this redeem script. And so the first copy would be stored temporarily. The second copy would be used to the op hash operator here. If the hash matches up to the redeem script hash that's stored on a blockchain, then what happens is it will start evaluating the script sig, or the redeem script itself. And it'll continue going with the op equal, and it'll keep going until it reaches to the very end, where again, either it's a 1 or it's not a 1, right? So we're at the end of the day, we're just looking for the stack to evaluate to a 1. So how we're actually doing it can be fairly creative and ingenious. So one benefit to the page to script hash is that you can actually reduce or shrink down the size of a lot of your more complicated locking mechanisms. So if you imagine all of these operators, all of these pub keys in the multisig, like you can have as many pub keys as you want, but with every additional pub key that you add, it actually will increase the size of your transaction, which in Bitcoin Cash actually the fees are calculated based on byte size. So the larger your transaction, meaning the larger the byte size of your transaction, the more you actually have to pay, right? So that means if you actually can create a transaction that's like small enough, you'll be able to get away with paying very, very little fees while having all of these complicated script operations. So this occurrence page, I won't go into too much detail because we already looked into it. I do want to just highlight the number 9 right here, op return and then op data. So this is actually something that's very interesting. Op return is an opcode that actually allows you to store arbitrary data onto the blockchain. So on the stack operator, when it sees that there's an op return, the transaction will still mark it as valid, but it just won't carry forth with all of the other data that's actually behind it. So what people can do is, it's like storing, like write a message onto a blockchain. If you want to store other sort of data, if you want to be storing an image, it will take you a lot of storage space, but you can be storing all of this information onto a blockchain through these op return calls. So in BTC and Bitcoin Core, the op return size, I believe it's around 40 to 80 bytes. In Bitcoin Cash, one of the things that they've done as part of the upgrade is to actually increase it to 220 bytes. So you basically more than triple the amount of space that you actually have to work with. And Bitcoin SV, they went super into the deep end with over 100 kilobytes worth of data. If anyone cares to figure out how they do it, you're free to do so. But yeah, essentially it's just to highlight that, this opcode could be used to store a lot of interesting data. And we'll actually go through some of this right now. But before I do that, I just want to ask, does anyone want to just take a pause right now, just like review some of the content, or you guys just want to continue?
I don't see any questions here, but if you wanted to do like a speed run of what you've covered up to now, I think that might be helpful. But
Sure.
I don't see any questions here.
Sure. So why don't I do this? Why don't I jump quickly into the code here and just show you guys what some of these applications will look like and refer to the stuff that we've talked about up till now, right? So we can see that this is this is a JavaScript application that I just whipped up, mostly for testing purposes, and we can see here for a lot of the things like creating the wallets with the words and whatnot, the derivation path for generating which path you're actually going down to, and then creating the key pairs for the public and private keys. So you guys can actually take a look at some of the examples that are also found online. I'll just jump really quickly into those. So if anyone can view this, yeah, I think this is big enough. So this is actually a repository dedicated for creating these kinds of applications, the SDK. And on the example page for the permissionless software and foundation, you can actually go through and copy some of the code that you want for, let's say, creating a wallet, right? So actually go through all of the working steps for creating your own wallets here. And you can change all these values you want to whatever desired outcome that you want. And there's also like splitting UTXOs, as we mentioned. The UTXOs is very interesting in that when you use a wallet long enough, and if you're going to be reusing addresses, the UTXO gets really, really out of control. So that's part of why like people typically just like to use a different address to be managing all the stuff. Another reason is, of course, it's for more privacy on the blockchain. So again, you guys could check out this repository, Permissionless Software Foundation. They have, again, working examples of code that you guys could just copy or download and just start running without basically changing a thing. So that's something to take a look at. We'll go through this section a little bit later on. I just want to show you guys the process of creating a transaction, building a transaction with the inputs and outputs. So here we can see, like we're obviously trying to find the appropriate UTXO or unspent transaction output, and we're tracking all the data that's relevant to it. And then the transaction builder here, we're actually going to be adding the inputs like this. And if you have multiple inputs, you'll have to be adding them one at a time, or be writing a code to be automating that process. One thing to keep in mind too when you're adding the inputs is that you also have to be signing the input that you actually added in. So here the 0 is actually referring to the index value of the inputs. So when you have multiple inputs, you're going to have 0, 1, 2, 3, 4. So this one basically just indicates which input you're going to be signing. And then afterwards, once you have this signed transaction, you're actually just going to be creating this transaction hex. And once you have this hex, you can actually just broadcast it out. So I'll just quickly run a quick demo of this. Let me check which address it's going to. Okay. So here you guys can see when I call this code up. Oh yeah, right here. So it'll show the.
Sorry, Jay, can you make that a bit bigger for us, please?
Hang on a second. Whoa.
Beauty. That's awesome.
Okay, that may be a little bit too big. Okay, hopefully this should be fine. So yeah, so what we're generating here is a whole bunch of information that's related to this transaction. Again, we're sending a P2PKH transaction out there. So we're going to need the public key hash, which is this value right here. And we can see that there is a whole bunch of balances and contract balances, which we'll get into a little later on. And so here, when we did the signing for the transaction builder right here, this gave us this really, really long value. Sorry, this long value right here. And when we actually go ahead to broadcast it, let's see if this transaction will actually show up as valid. Yeah, it's looking good. So this is the balance. This is all that. Oh yeah, okay. So unfortunately, this is still in confirmation phase. So some of the information won't be populated until it's actually part of a mine block. So currently it's just in the mempool. But we can actually see that there is information being recorded down here. So it's just a matter of time before it confirms.
So you just broadcast that transaction from your terminal there, and we're just waiting for it to be confirmed?
Exactly.
Very cool.
And so if you guys actually see right here, there's actually a whole different ways of doing the signing. And I guess we could go into this real quick. So the way, I don't know if I understand all of this correctly or 100%, but effectively what I basically understand it is that the typical way we do the signing is with the sig hash all, which means that we're going to lock in all of the inputs and the outputs, and so that no one can make any changes to a transaction when we generate this hex value. So there are other ways of signing where we could potentially just sign a portion of the transaction, meaning that other portions like the inputs or the outputs, depending on how we sign it, could be changed, could be added, could be manipulated, could be whatnot. So that's basically what you see here in the transaction builder with the different hash types. So I guess I'll just highlight the one right here, which is sighash single and sighash anyone can pay. And again, if anyone wants to take a look at this, you could just go on, just Google sighash Bitcoin signature types. I'm sure you guys will be able to find it. But what this sighash single and sighash anyone can pay does is that it will lock in just like the input that it contains and the corresponding output that it contains. Meaning that you could potentially just lock in, let's say I have $100, I want to send it, or at least $50 to Joran. But this transaction would be part of all of the other transactions, or like other transactions or inputs and outputs that other people want to send out, kind of like how a bank would do its settlement at the end of the day or at the end of the period. So when you have a signature that's using sighash single, sighash anyone can pay, what happens is that, again, you're just locking in the inputs and outputs that you specified here. And that if someone were to take the raw transaction value right here and actually start to add in more inputs, add in more outputs, it's actually allowed because it's not touching the inputs and outputs that you specified. So that's fairly useful, and a lot of people are actually looking into these kinds of different sighashes for creating things like derivative contracts and other payable transactions and other formats like that. So hopefully that's a quick overview of.
Sorry, could you go over that one more time? Because it seemed like if you added on, say I added on no, I get the money. So how does that get protected there?
Yeah. Okay. So so this is where I'm not too sure exactly how it's done, but I believe what happens is that if you want to lock in the inputs and outputs that you're looking for, it'll do a different hashing operation than, say, if you were to keep those sections open. So I believe if you want to lock it in, it's going to be like a regular transaction hashing, the SHA-256 and whatnot. But if not, I believe what happens is that it just leaves it unhashed so that other people could add in their information and then hash everything afterwards.
I see. So this is not a normal transaction. Like I want to send X to Y. This is like a special kind of thing that can be manipulated on chain. So not the most secure way, but has its benefits.
Yeah, there are definitely some of these signature types where it's definitely not safe. So for example, I believe sig none. Yeah, sig none is basically saying, hey, if anyone wants to change it, go ahead, right? So yeah, there are some signature types where you want to be careful with, but it's kind of like a give and take, right? You need to really understand what is actually going on, which sections are being locked in, because you can definitely imagine, like, if you were to build something like an exchange or like a decentralized exchange, you want to be able to add in these inputs and outputs, but you don't want those people to be saying, hey, I have this hash now, let me just go ahead and spend it or change it however I want, right? You still want the funds to go to your destination that you wanted originally.
Very cool.
Yeah. So that's just a quick demo up to this point. Yeah, I'll talk about the pay to script hash and how to construct that a little bit later on, but this is basically to just highlight how you do the most basic wallet transactions. And of course, if you want to add in more logic, like calculating how much fees you want to give out, there's a lot more things that you could do in there. So let's just jump back into the op return stuff right here. So this is very interesting in that because now we have a way of storing data into it, we can also create rules or like MEETUP rules to say, hey, we see this data. Is this transaction following the meta rules that we set for ourselves? So one example of this, and this actually came out fairly early on during the Bitcoin Cash development phase, is something called memo.cache. And this is basically the on-chain equivalent of Twitter. So using the 220 byte size limits, people are actually able to append different messages to that transaction. So when you see all the inputs and outputs, one of the outputs will actually be the op return with the message that you actually want to be writing. Now, memo.cache isn't the only platform or the protocol doing this, but they are one of the first ones. So that's why they kind of get a notable mention here. But essentially, the whole point of the whole idea of this is just to be reading the blockchain data and just be and taking actions afterwards. So for Twitter, for a social media platform, you have your basic action sets like create your name, determine what your name is, writing a post, replying to other people's posts, liking someone else's post, if you want to set an image for your profile. And all of this is, again, done by using the hexadecimal format after the op return. And the way that memo cache does it is that it'll actually ask you for the action prefix followed by the data payload of what the action is supposed to be referring to. So what that will kind of look like if you break down the op codes, the hex values. So 6A here corresponds to the op return, and then 02 is just referring to how big the next data size is, which is the action prefix. And so there's 2 bytes here, the 6D, and the 01 are 2 bytes. So that's what the 2 here stands for. And we can actually see that there's another payload size after action prefix. 08 here, I believe this is actually 8 in decimal and in hex decimal. So there should be 8 sets of these numbers corresponding to a payload. So you guys can kind of see, like after the 60 and the payload size, everything else is very much arbitrary. And so while memo.cache uses 6001 to be set name, you can actually make your own platform. You can make your own application whereby you can say 5F the 02 is the action prefix or anything like that. And what you actually find is actually down in the more protocols in the GitHub link down here, member app is actually taking the memo.cache idea and just adding more features into it, right? So just to show you guys what some of the user interfaces would kind of look like. So this is, nothing on here would suggest, this is anything blockchain related. But in fact, what happens is that this application, this front end is actually just pulling all the data from the blockchain and processing it appropriately so that you'll know that, let's say, Telis4 is actually the name of this address or corresponding to the name of the address. And this is the actual post. And then we see examples of replying to different other people's posts and stuff like that. And then, here right below it or right next to it is how many tips, I guess, has been sent out to those posts. So if we take a look from the UX, the UI to the Block Explorer section, we can actually decode this entire transaction into what it will actually be comprised of. So here we can see the big op return that's that's storing all of the data, which I guess would be this very long thing. And then the index 2 for the vouts would be to essentially send back the remainder of the balance back to the address that this person free trade, back to their address, basically. So yeah, that's basically how all this stuff is presented. Now, before I move on, I do want to know that, again, like, once you have the information available on like some sort of Explorer, you can change the interface to be whatever you want. So what you see here, it's laid out kind of like Reddit, kind of like Twitter almost. But you could change it to, be something like Pinterest or whatnot. It's just a matter of changing the user interface, right? And what a lot of like people and developers in the space aren't really getting is that, while the technical portions are nice, it's also equally important that when you're building applications, that it's very, very intuitive for your end users, especially when your end users are not very blockchain savvy. And I guess, Jordan, if you could just add in a poll saying like, if you have you ever made a blockchain app or a decentralized app, that would be good, just so I can get a sense of things. So yeah, I'll quickly move forward. So at this point, some people may be wondering how exactly would these data actually be processed and be read. And so this is where something called Bitdb kind of comes in. So what Bitdb is basically a Bitcoin database, as it says right here, whereby it stores all of the transactions onto the MongoDB database, and then it provides a query system so that you can actually specify specifically what type of transactions you are looking for. And if there are transactions that don't follow these criteria that you set, it will basically just filter them out. So here, what happens is, let's say you want to find solve a query whereby you want to find all the transactions that were made by this address after a certain block, right? So what you actually do is create a query that's very, very similar to this, in which case you'll have all these different values for the query, and then you'll have the result output, so how you want the output to be formatted. And so here, so what this query is doing is it's going to be looking for transactions with this address here. And in the output for the vouts, it's going to be looking for something like a 6D02. So if in the output indexes, if one of them has the 6D02 in the first byte position, then it will basically say, yes, this is one of the queries that you're looking for. So I won't go into too deeply into how the querying system works. It's best to do your own documentation work on this. Partly because not many people actually develop on it. Partly also because this requires some sort of an application for people to actually use against, to be querying against. So memo.cache is a fairly good example where all you need to do is by querying the action prefixes of a particular address and then parsing all of the actual responses that they gave out. So yeah, so this querying system is called JQ, and it has like all these different rules that you can read up on this link down below. And if you don't want to go through all that process, you can actually just go to one of these Bitdb Explorers that you can find online. This here is using the bitdb.bch.sx. There's quite a few other people and other organizations who have hosted their own copies of Bitdb. And yeah, essentially, you could just be popping in all of the querying that you're looking for, and then it'll just spit out the response that you're also looking for. So here we can see, again, the block index, what content you're actually looking for, and the timestamp, or I believe this is the Unix timestamp that's universal for all the computers. So here you can already see, you have most of the tools available to be building out these kinds of applications using this kind of querying system. It's just a matter of knowing which data you're looking for and processing that query. So before I move on, does anyone have questions, comments?
I think this has been info packed so far, and I'm following with you, man. I've been asking questions as they came up, and I don't see any questions in the chat or in the box. But then I've also been dropping the links. I've been quickly Googling while you're mentioning them and finding the links for folks and dropping them in the chat. So if they watch it afterwards, they know exactly where to go.
Cool. Okay, yeah, that's fine. So yeah, that's that's basically Bitdb. So again, if no one has any questions, we'll get into some of the more exciting things, particularly with SLP, right, and Simple Ledger Protocol. So I think it's safe to say one of the driving factors for people going into a lot of these blockchain and stuff had been the idea of these getting these coins or these tokens or whatnot, and of course you want to get them for the purpose of getting more money out of it. So of course in 2017 there was a whole hype buzz around Ethereum because at that time people were able to create these ICO tokens or coins and actually be able to sell them to people online on via the blockchain. So while I don't think we're at that stage yet for these kinds of token systems, it's Simple Ledger Protocol actually does bring in something rather unique to a lot of the previous attempts at creating these kinds of tokens and coins. I'll get to this slide actually a little bit later on, but I want to jump into this slide right here. What SLP does that's like very, very, at least I haven't seen any other protocols try to copy or emulate it, is that it uses the UTXO model that's existent on the Bitcoin Cash protocol, the platform. And what it does is actually it combines with the Bitdb to actually trace the specific subset of the SLP transactions that you're looking for. So in other words, all of these transactions are actually going to be valid Bitcoin transactions for the SLP side. But sometimes if you create an SLP transaction incorrectly, it'll still be marked as a valid Bitcoin Cash transaction. But through the Bitdb, through the querying rules and through all that stuff, you can actually filter out which transactions are not valid to your specific subset of the SLP transactions. So this is really useful, again, in that you're not taking up resources that's existent on the blockchain network, right? You're not asking any of the nodes to validate this SLP transaction for you. What you're doing is using the same UTXO model of validating whether a Bitcoin or a Bitcoin Cash transaction is valid based on its genesis block or its creation block. And so in the same way that the Bitcoin Cash does it, SLP tokens also do the same way. The first transaction for any SLP token would be a genesis transaction, whereby it just basically marks that, okay, yes, we've created a new token here and has these kinds of properties that's written in the transaction itself. And you can see here there's a whole bunch of different transaction types, mint and transfer. And they basically all have to chain back to the genesis block in order to be marked as valid. So just going back to this slide here, the four main SLP transaction types for the outputs are, again, the genesis, mint, which is basically increasing the total supply, the total amount of coins that we have here in the SLP. We have the send, which is, again, just sending the SLP back and forth to one another. That's kind of like the whole purpose of these tokens. And then the last one is burn, which this can actually be done by two ways. You can actually specify that you want to create a burn transaction, or you could just create an improper transaction output, whereby like maybe a part of it, a part of the SLP send out that you want to send is valid, but part of it might not be valid. And we will go into how that actually comes about a little later on.
Quick question there. So are
Yeah.
these analogous to ERC20 tokens, or are they something different?
So you can think of them similarly to ERC20 tokens. I guess the main difference is that you don't have to be creating a contract per se, right? You don't have to be funding the contract to be generating these tokens per se. All you need to do is just pay for the fees as you regularly would for making a typical transaction. So it's not like the smart contract address for ERC20 token is like very, very autonomous. Like when you pay into that address, it will actually do something back. In this case, because we're just relying purely on the UTXO models, a lot of those other operations that a lot of the developers want to put in will basically have to be done on some sort of like a backend server that, while you are using a server, anyone could, in theory, just spin it up themselves. So that's kind of like the main difference, is that the ERC20 really is like, it's fairly heavy on the technical requirements, whereas the SLP is fairly light.
Okay, so you're broadcasting a transaction that acts as a genesis event for a new token that is going to live on the Bitcoin Cash network, and you can verify that these tokens were created fairly by tracing back the UTXO model.
Yeah, exactly.
That's
And
amazing.
these transactions here, they don't have to be in like one block right after the other. You can have the Genesis transaction be one block, and then 5, 6, 7, however many blocks later on, then you could be doing all these operations afterwards. Does
That's
that kind of make
amazing.
sense?
Yeah, that's really cool.
All right, awesome. Just want to check where I am here in the slides. So this is just an explorer that you can actually find on the Simple Ledger block explorer. They've actually created a custom block explorer specifically for finding all of these SLP transactions. And here you can actually see that they have a very, very nice graphic for showing where the SLP inputs are coming from, and if any, where the outputs are going to. So this obviously is an older transaction because it's already sent out all of these coins. But it's still nice to see visually how all of this stuff is actually tied in together. Okay, so how do you actually construct a transaction? So again, if you guys do have questions, please just post in the chat, or just raise your hands or something, anything like that. So creating these transactions. So a Genesis transaction will have the following spec. So what the hell is all this, right? So here what we're seeing is basically the array of the outputs that we're specifying in this transaction. So ignoring the first index, the vout0 for now, we can see that there's a 1 to m, and then there's a whole bunch of other address outputs afterwards. So let's try to break this down step by step. So in the first one, in the vout of 0, we have the op return. And in the specification page hosted on the Simple Ledger's GitHub site, GitHub page, I guess, they'll actually go through how all the transactions will actually be created. But I found this chart to be rather helpful in that it just straight up tells you what the protocol is actually looking for. So right after the op return, we can see there's something called locat ID, which this, when translated into the hex values, will always be a certain value type. so that when you're going through the Bitdb process, you can actually just see if the operator contains this ID value. And if not, then you can just automatically ignore it. So token type here, most of the tokens that you see are something called token type 1, which is the Genesis, Mint, Send, and Burn set that we just talked about. Transaction type, again, you'll just be writing in Genesis as just plain text like that. And so you go through all of these values, like the ticker, the token name, any other metadata that you want to attach to the token, decimals, and initial token mint value. So all of this data is going to be recorded as the first transaction output after the op return. And so this is where all that data is actually stored in. One thing to keep in mind is this, mint baton vout parameter here. And the way that the minting works is that you actually have to spend the mint UTXO that you get from the Genesis transaction. In other words, if you want to create an SLP token where you can increase the supply later on, you'll have to indicate that this mint baton has to be some value that's not 1. So you can see all the specifications right here. It's either 0, which also corresponds to this op return, which you can't spend anyways, or it'll have to be in VL position 2 to infinity. Or not infinity, just FF, whatever that value is. So when you do want to create a new mint token, you want to mint additional tokens, you have to specify that this is the transaction output index that you want to be sending from. And I guess the same is kind of true for the send transactions. But again, this is just the Block Explorer page, what it will look like. So here we see what the send transaction output would look like on the op return. It's very, very similar to the Genesis right here. We can see some of the similar stuff like the locat ID, the token type. Transaction type here, instead of Genesis, we say send because we want to be sending these tokens. And right down below, it's actually the token ID. So this token ID is actually the transaction ID for after broadcasting this transaction Genesis onto the blockchain. So we can see here in this blockchain example that the token ID is actually the transaction ID of the token that we just made. And when we're going about to make, let's send a transaction with that newly created SLP token, we have to specify that what token are we actually going to be sending from, right? So because every single SLP token will have their own unique token ID, you need to be tracking which token set that you're actually sending. And yeah, and then afterwards you can specify the outputs, which will actually correspond to the output indexes that's laid out down below. So you can see however many outputs that we have here. Here's maximum, apparently it's 19. So you can go from 1 to, well, I guess in this case would be 19, but it would just be whatever, however many token outputs that usually correspond it to. Yeah, okay, so once we have like these kinds of transactions set and we have the blockchain data, where we have a way to read the blockchain data, we can then start creating these kinds of interfaces to better represent these kinds of SLP tokens. So Spice here is a very, very popular SLP token. They've actually created their own social media network called Spice Network. And you can actually just be posting whatever random messages that you want, and people will actually just be tipping you in these Spice tokens. So this operation can be better seen in some of the Telegram groups if you guys are in those. There's a Telegram bot called SpiceBot, where if you just reply to someone's comments with a few peppers or whatever their icon is, it'll actually be tipping out those SLP tokens to the different users. So this is very similar to the early Bitcoin tipping bots that one could have seen in on Reddit and Twitter and stuff like that early on. Instead of using Bitcoin or Bitcoin Cash, of course, it's using a Meta protocol token. In this case, Spice. So, okay, yeah, I guess I can jump into the next section here. Yes, the spice must flow. Whoever said that is excellent. So we've seen how some of these applications could be built with a combination of writing data onto the blockchain and then using tools outside of the blockchain ecosystem to then better parse it and then present it to your end users. So we're really trying to take advantage of the application architecture that we're given with here. So you guys may recall the pay-to-script hash that I mentioned when talking about the different transaction types like P2PKH or multisig. Cash script is actually a tool that came out, I believe it was last year. And it's not the only compiling tool for Bitcoin Cash. I believe there's also, there's also something called Spedna, SPEDN, which does something very, very similar to what Cash script does. But essentially, the point of Cash script here is to really try to emulate what Solidity on Ethereum does, in that you're able to create these kinds of smart contracts on Ethereum with Solidity, right? Well, instead of creating these smart contracts where there's a virtual machine to do all the operations for you, Cash script, what it does is it will compile your code down to the byte format, the hex byte format, and then it will just basically prepare for you so that you can call upon those contracts anytime you want, with the inputs that the functions have specified. So it's a tool that comes in two sections or two packages. The first package is the cache compiler or cache script compiler. And this, again, will compile your cache script file into the appropriate interface for all the interactions. And then secondly, you'll have the cache script SDK, which is the developer tool for actually making applications and interacting with your compiled contract artifact. So you guys could go on cachescript.org, and actually I'll just quickly jump into what this site kind of looks like. So again, there's a lot of documentation on this website right here, where you can go through, for example, a sample code, cache script code, that you can just basically copy and paste. Maybe you have to change this to a 5 or something like that for versions. And then here you'll see how you integrate it with JavaScript. So if you're not a JavaScript fan, that's not a problem, because what this does too is it actually creates the artifact for you. So with this artifact, and I believe I have a slide on this, but the artifact here is basically in kind of like a very generic interface that any programming language could use, and it's just basically for compatibility's sake. So what it will actually store is your contracts, the name of your contract. It will be stored here, all of the inputs and all of the different code that you can actually call up. And it'll have all this information available so that, let's say if you really like Python or C++ or Java or Rust or any other languages, all you need is the artifact file, which it will come in JSON format. And then you can just take that and start calling the functions that's stored onto these contracts. So the artifact specification is fairly cool, and Yeah, it's very, very similar to the Ethereum, the Solidity's ABI. You can kind of think it's kind of like the equivalent of that.
So is this artifact stored on the blockchain?
Yeah, so this artifact here, if we just go to the examples, so the contract is up here, the JavaScript file is up here, down here, and what actually happens is that I don't know if you guys can see this, but hopefully this is big enough. It'll actually compile the cache script contract. So you can compile it differently, but it typically is not stored on the blockchain. I have played around with storing the artifact itself on IPFS and then pulling it that way. But again, like just storing on the blockchain itself is quite expensive, and sometimes it just exceeds the size that you have to work with. Um, so yeah, these artifacts are typically not on the blockchain, but there's many different ways of sharing it, of course, and it doesn't really impact the performance of the blockchain network. In that, like, it's not like in Ethereum where, let's say, CryptoKitties was able to just bring the Ethereum the Ethereum blockchain to a grinding halt. There's nothing like that with CashScript or in BCH, right? It's just basically helping you compile your contract here with the different functions and compile that into the bytecode where then you can process it through the P2SH transaction type.
Okay, so the contract is stored locally in your app that you've created, and all it does is help you to like construct the correct opcodes to perform the action that you want to perform. Is that correct?
Basically correct, yeah.
Sweet.
So when we're creating the contract or a new instance of a contract, we'll be putting in the artifacts. We'll be putting in all of the constructor values for initiating the contract. So that would be put in an array here, and then we'll have a provider just to basically say, which network are we on, right? Are we on the mainnet? Are we on the test net? All that kind of stuff. So yeah, the SDK is the CashScript SDK is written unfortunately in JS, but yeah, if you do want to, you can definitely write your own developer kit for interacting with a compiler yourself. So yeah, that's basically what this line here with the new contract does. And once we have this contract instance, we can just start calling the functions that I have. So the two functions that I did have here is again the transfer and the timeout. So in the transfer section, we're just calling after the function, we're calling the transfer, and we're creating a new signature template with the right key pairs so that we can unlock it. And then we will specify what's the destination for the funds afterwards and what's the balance, and it'll just send. Something very, very similar when you're calling the timeout function instead of transfer, because the parameter here is the same. You're asking for a signature. Nothing looks too different, but yeah, essentially, if you have more and more complicated functions like that, you just basically be calling this and then adding in all of your parameters one by one afterwards.
Is that using Web3.js or another library?
It's not using Web3. It's using this is a dedicated library called CashScript.
Oh, okay, I see.
Yeah, so if you go into this is too big. If you go into getting started, you can actually see how to install the CashScript stuff into your computer. So this would be to install the CashScript compiler, and then here would be to install the CashScript, the standard developer kit.
Cool.
So again, as I mentioned, the compiler here, in theory, it should be compatible with all these different languages. It's just that the JavaScript and TypeScript is the first one to actually be using CashScript like this. But again, nothing stopping people from developing like a Python SDK for the same thing.
Sweet. Are you giving people ideas for the hackathon?
Oh, we will get into that. We will get
No, I
into
mean,
that
like
real soon.
if someone wants to make a compiler, that could be for another like common language. That could be a project right
Yeah.
there.
Yeah, so there's definitely a lot of things that people could do in there, and I'll show more of the examples a little later on. I just want to go through the different steps again. Um, so yeah, like if we have the P2PKH contract, you will see there's a function called spend, and then it's requiring all these things. And if you actually take a look at these lines, it's very, very similar to how the regular P2PKH will work. First, you're going to check if the hash of the public key is matching up to the public key hash that was stored when you created this contract. And then after this step is done, you're going to check the signature and the public key pair. So we can go back a little bit later on, but this is basically the exact same steps that the regular P2PKH is going through, except for one caveat that it's still using the P2SH model of evaluating the all of the bytecodes. So it won't look, when you look at the raw hex for a transaction like this, it won't look exactly like the P2PKH. And there will be tools to actually show you how to actually look into that. So I won't go into this part right now because we just went through that. I just want to, unfortunately, this is a little bit small, so I'll just use the web page version. This right here is the build and the meet. So, so here we have basically two ways of, well, actually, there's a total of 3 ways of what we can do after we've finished preparing the transaction. Of course, we can send it, which means once we have all the stuff done, we just broadcasting it onto the blockchain to some node. And you can see here the example of that, right? Many times, however, we don't want to be immediately broadcasting a transaction after we've finished building it. There could be some things where, some situations where we may want to add in more inputs or outputs, or other things like that, right? If you just want debugging purposes. So the build function right here, or call right here, can be used to basically just return the raw hex string that we created for this transaction. So once we have this hex string, and depending on how we did the signing for the transaction, we could then import that this hex string into some other function to then start adding in other people's inputs and outputs, kind of like that. The third one is actually more dedicated for debugging. And unfortunately, I will not be able to show an example of this too well on Windows. This is built mostly for Linux. It's a command line, it's a terminal command line interface where you can actually go through all of the different opcodes one step at a time. And I'll just show you guys what this will look like. You can actually download this MEEP tool. There are a whole bunch of releases that you can just directly download, unpackage. Maybe there's like some installer files in here as well. But essentially, what happens is you're going to be given something like this, like a MEEP debug and then transaction, blah, 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 blah. And so once you put that into a terminal, something like this will open up where you'll see the script sig, which is, again, the key or the inputs that you're putting in. The script pub key, which is the lock that you're trying to unlock. And then here is the redeem script, which is part of what's like basically all of this, all of the redeem script, when you hash it together, should be equaling this C9C, whatever, blah, 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 blah. And so again, let me actually see if I could do something here. Yeah, I was trying this earlier, but I don't think I'll be able to. Yeah. Okay, so let's just pull one of these examples, and I'll show you what happens on Windows. just so you guys can avoid it. But it's functional and everything. It's just a graphical bug or incompatibility or something like that. So we can see here I'm calling the MEEP app, and then we're calling in the debug, and then whatever the transaction is, just like the examples we see here. And hopefully, let me see it. Just give me a second. Debug. All right, here we go. So obviously, you guys can see the Windows screen for this. It looks nothing like the Ubuntu screen for this. But yeah, like what basically happens is you press F3 and F4 to go through all of these stack items one at a time. And if there's any errors or anything like that, it will just pop up an error message for you. So let's just go through this real quick. F3, F4, 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 F4. You can see there's more items being put onto this box here, which represents the stack, right? So all of this, and then it's doing some evaluation. So this tool is very nice to help you debug your transactions, especially during the locking portion of it, to make sure that you have the correct setup in place. If, of course, in this case, it's a success, but if it's not a success, it will actually just tell you where that error is coming from and all that kind of stuff. Cool. So cool. I'm back. So if anyone, again, wants to play around with this, just go to gcache/meep on GitHub. They have a release section on the right here where you can go and download. Or if you're really a technical and pro, you can try installing this yourself with Go. So let me just, where's that screen? Where's that screen? Okay. Yeah. Okay. So I just went through all that. Yeah. So some of the other stuff that the cache script offers is the ability to basically really control the kind of output transaction that you're looking for. And so here's a whole bunch of different transaction options, where you obviously the regular like to, where you're sending it to. And then you see like with the operaturn, so that you can be writing in all your operaturn data, kind of like here, we're writing a memo.cache post. And so now you can see there's a from, right? So there's a to, so that's the v out. The from would be basically where you're paying from, or the v in, right? The input values for the Utxos. And this function here is basically needed if you're going to be doing cache script with SLP transactions. Because again, SLP transactions require that you track the UTXOs that you're spending in each of these. And yeah, you'll just be putting them in one at a time, like that. Here's some other options where you can set different fees. You can set how long you want the transaction to be locked in for. So you can say, for example, you want to lock a transaction for, let's say, 10 blocks. Right? You would use something like with age or with time to basically lock it in using these kinds of transaction TXHs for the regular time locks. So again, I would highly recommend just going through the different documentation that we have. These links should also be available on portal.blockhack.ca. So if you haven't done so already, be sure to check out the resource page that we have there. And yeah, so that's really like the from section right here. this part, what they call the global covenant variables, is I believe this was something that was introduced actually for when Bitcoin was actually trying to introduce SegWit for the first time. And the whole idea here is we want to create a copy of the transaction that we're preparing to send out, and we want to take that transaction image and put it into this contract so that we can see, well, or basically we can get the contract to recognize what its current status is. So, for example, we have values here for what kind of inputs that you have here, right? With the hash outputs and sequence, and we can have previous cells, and then we can have the hashes for the outputs, which means you can actually check if the outputs are what your contract is actually specifying. So I won't go into all of these different values in the sighash pre-image, or again, like just the image of the transaction before you send it out. But one of them is actually fairly important.
Is that a way for you to like test? Like it's a test before you go live kind of thing?
Pardon?
Is this a way to test your contract before you deploy it?
Oh, so this is a way of getting the contract to basically know itself. So without all this data, the contract wouldn't know like what kind of inputs it has, what kind of outputs, what the UTXOs, like any of that other data that we will kind of expect from a blockchain indexer or something like that. So through this method, we're actually going to be feeding in all of those values. And let me see if I could just open this up here. Yeah, because again, I do apologize. The slides have the text fairly small. But yeah, global covenant variables. So what we're really looking for in a lot of these right now is just basically trying to make sure that the transaction hash outputs that we're setting is going to match what was specified within the contract itself. So you can see here in the transaction hash output, we're actually going to be sending into the contract a copy of all of the outputs that we actually created, and just going by the contract to say, hey, are these outputs what the contract was looking for, right? So you can see here down below in the examples section, there's two lines here, the output 1, output 2, creating two different outputs. And then what we're doing here is we're basically hashing these two outputs together and seeing if this hash equals to the like what we got in the transaction hash outputs for when we're preparing to send the transaction. So this is really just a way to let the contract know what its current status is, what kind of transaction it's about to send out, and all these kinds of like just try to make it self-aware, if that makes any sense.
Yeah, it makes more sense. Maybe trying to draw correlations to things that I know. Is it kind of like how TypeScript knows what type of output to expect?
Yeah, basically.
Okay.
So yeah, it's just sending a copy of like the transaction that you're expecting, and taking that data and then doing more operations within the script itself, within the cache script itself.
Very cool.
So just going back to the slides here, there's three main different types of outputs that we could be creating. The first one is the output P2PKH. This is the most standard version. Then we have the P2SH, which is pay to script hash. And then lastly, we have the output null data, which again is for the op returns. And in order to like basically make sure that the outputs are all are exactly as we want it or specified, it will just have the require all the outputs, the hash of all the outputs to equal the transaction hash. The TX is the pre-image hash. We're getting to the end of it, actually. So actually, I'll put this link up for now. If anyone wants to take a look at them, there's a few links here, like cash.coin.dance, that tracks the various development portals. There's also the link to the cash script stuff, as well as the Bitcoin, the SLP information. Developer.bitcoin.com has a lot of the basic tools for like just getting started, especially with the SDKs and stuff like that. Although I do think they've changed some of the content recently. So I'll just leave that for a few more seconds for people to take a look at, and just jump into the examples that we have here. So if we go to bitcoin.com/castscript, the repository for it, you can actually see, here's the compiler and the cache script SDK all here. But it also has this example folder where it's very, very helpful because like you have all these working examples of code. So for example, here is the cast script for P2PKH. Here's another one. This is the announcement, which is the example that I had at the very end. What this is doing is essentially creating a message, in this case, a contract, whatever, blah, 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 is creating that memo.cache message post. And then it's going to calculate the appropriate fees in a very rudimentary way that you would actually be paying out. And then finally, it's going to check if the output that you created for this transaction is actually matching what this contract is expecting. So if we jump real quick into, so that was announcement.cache. Let's just jump into the announcement TypeScript file. So as you can see, very standard setup, creating all the wallets, all of that nice stuff, which is fairly standard for most apps. So now we go to creating a new provider for the contracts. We're creating a new instance of the contract with the artifacts right here. There's no constructor parameter because there should be none. And then the provider is the mainnet that we connected to. Just want to pull the examples up again just to double check. Yes, indeed, there are no constructor inputs or parameters, so this should be empty. And so here we can different addresses, all that kind of good stuff. And here we see where the pre-image, the sig hash kind of comes in that we're calling the announce function, which is the only function that we have here, with the op return, with the hard set fees, all that, and then send. And what's nice is that I guess this is updated, but there's actually you can actually set the hard-coded fees so that it'll automatically generate the transaction output to return all of the funds back for that remainder. So here you see just the op return with the data right here. And then here what we're saying is we're going to pay a fee of 2,000 Satoshis. And then with the min change, we're going to require that the change address for receiving all the remainder will have to have a minimum of 1,000 Satoshis at the very end. So if there's more than 1,000 Satoshis, great. If not, something happens here. So yeah, that's basically what the requirement here does. We can actually do more complex stuff. So this is actually, yeah. No, sorry. This one. So this contract right here is I don't know how to pronounce this, Messinas or something like that. But it's essentially a way to try to donate or pledge money in for a project. And so you can see all of this stuff right here. And then what we're doing is if the value is less than a certain threshold, we only want to just create one output with no change recipient. If it has more than the certain threshold, then we want to be creating a second transaction output, a vout, where it will send the remainder of the balance back to the contract address itself. So on the documentation, this is how you actually do the how you actually determine the contract address itself. And so when we have all this together, we can say, hey, is the transaction output as we specified here? And if we just go to this one right here, yeah. So yeah, we'll see that it'll have one receiving address at the very, very least, and it'll have a hard-coded fee of 1,000, which is what the contract specified. And then any other balance, if this balance here is more than what is actually available or is under the threshold, then essentially there will be no change recipient automated here. And that will basically just match up with what the contract was looking for to begin with. Right. Okay, so I want to show you guys some of the code that I've got here. So I did a basic operation to send some funds. So you guys all saw that transaction hash, transaction text go through. Where is? There we go. So let's just go through how the cache script will actually go about building all this. So we have two calls right here. I guess I could just comment out one of them for now. And so we'll just focus on the first one. So this one right here is creating a P2PKH, which is this file right here. So again, this is exactly what you guys just saw. And so it's calling the spend function in the P2PKH right here. And it's going to send it to another contract address, actually. And we're going to build that, yada, yada, yada. So let's try to actually, yes, let's try this. Comment out, comment out. All right, I think that should work. So if I call this function right now, so what I'm expecting is, okay, so we did have a raw transaction. Oh, that's right. My bad, guys. I just set it to build. Yeah, so again, you can build out the raw transactions like this, but I'm actually going to send it. You can also do the MEEP, which will give you the MEEP output for you to copy. But let's go with the send, and here we should get a transaction hash. Perfect, perfect, right here. And we are on the testnet. So we will go to the testnet explorer, pop it in, and we can see our transaction right here. So again, there's no confirmation because we just sent it, but we can see that it's the addresses that we got right here. So this is the address that we're looking at, and that's the exact same address that's laid out right there. And here we're actually, oh, okay, so there's some issues with the endpoint interface, but that's fine. We can see that the transaction has been registered with some of these explorers at this point. So that's the regular P2 PKH transaction type. I'm going to, yeah, that's fine. I'm going to show how to create something more complex. So here I'm actually going to be manually writing in a an SLP transaction, which here is the genesis. I'm going to send it to 2 instances. So here's a first contract instance, here's a second contract instance. And you can see we're actually using 2 different contracts for this. So let me just go to what the BIP38 does, this contract. So this contract is actually something that I created to generate new addresses by just inserting different passwords with the same key pair that you have as a base level. And so what happens here is that not only are we putting in the signature and the public key of the regular address, but we're also going to be putting in the password parameter here. And what this password parameter does is it's going to be taking the signed the user password, which is signed, and it's going to match it with the password that we just entered and provided here with the pub key of the owner. And we're going to see if this is actually the signature that the owner created. If it is, then obviously we can go through. If not, then it's kicked out, right? So because anyone could put in a different address, a different value here, you can actually set whatever address. You can actually change the address to be whatever you want. And so you can actually go about getting new addresses without doing all the derivation that's described in bit 44. So jumping back here, we're going to be putting in, we're going to be creating a password, which is a function call up here. We're going to be putting in the Alice's signature and the pub key, and then we're going to be writing all of this data. So let's just try sending it out. And we should see something very similar to a transaction ID. So here, instead of just a regular pending transaction, we can actually see there's more information popping up on the right side. So here it's validating that this is, in fact, a valid Genesis transaction. It has all of the parameters that we set here. The symbol is test, the token name is test token. So you can see that it all corresponds up. And we can see that all of the mint baton VOuts, the token balance holders and whatnot, they're all basically laid out there. So this is essentially just like one way of working with these tools. If you have like more complicated contract transactions, you just basically go through the same process. And I guess finally, I want to just show everyone one of the applications I've made, partly for this workshop, partly also for an organization that's looking to do more tokens with the Bitcoin Cash network. So hopefully this is large enough. So what's going on here is we're actually going to try to take the SLP concept and try to create non-fungible tokens out of them. And so obviously you can create non-fungible tokens by just having a token supply of 1. But there's also other ways of doing it. And I guess I'll leave that for the SLP guys when they're giving their talk. But if anyone is curious, the specifications for both the token type 1 and the SLP, the NFT tokens, are on the Simple Ledger Protocol's GitHub page. And so here you can see what the kind of differences in creating the NFT tokens. There are some changes to the token field type, but all in all, it's not too bad. It's not too different. So let's just go through what this would kind of look like, right? So we have in this code here, we have all of the necessary setup as we do. Here we have a function to create the accounts, to send out the transactions, create the transactions. And we're just going to break down all the different types of scenarios that we're going through. So unfortunately, this is not very pretty in coding wise. I much prefer this, like a lot of this, to be automated, but it works for now, right? So a lot of these things you got to keep in mind is still in active beta development. So use word of caution when using these things. So here's the contract, and I've actually already deployed it and put in some funds into it. So I believe I should be on mainnet. Yes. So we're going to go through all the steps of creating the NFT tokens. And here is just to show that I have enough Satoshis or balance in the account. And so does the contract address. So let's say with the NFT name, and let's just go back to this page right here for reference. So the parameters that we're looking for are the ticker name, the token name, the document URL and document hash, decimals, and how many tokens we want to be minting out. So let's say we want to create an NFT called, I don't know, block hack. NFT symbol is, let's say, BGH 2020, document URI, blockhack.ca. We're going to have decimal of 0 because we want to create an NFT token out of this. If you have a decimal that's non-zero, then you can't really create an NFT. So the initial token quantity will be 1. And then once we have all this set up, we're going to click the NFT parent genesis. And so here on the left-hand side, the right-hand side of the console, we can see the raw transaction. It's a little bit small, but this is basically the raw transaction that you generate. And then once we click send transaction, we can actually get an URL, which, if everything goes correctly, is going to show us here we go. It's the NFT token that we just created. So the name is blockhack, symbol BGH 2020. I don't know why the interface is not showing this, but you guys can see the tokens right here, the mint baton, and all of these different stuff, right? So now that we have a Genesis transaction with a balance of 1, we could do a few things here, right? We could now create a child Genesis, which means it's just basically creating the tokens out. Or we could create more parent tokens. And the whole point of creating these parent token, child tokens is, again, utilizing the UTXO models, whereby when you create a child genesis, you have to be referring to the parent token that you're actually sending from. So this provides a way of essentially creating multiple different like NFT tokens under the same overall brand. So if you imagine like a CryptoKitties, every single CryptoKitty would have their own child NFT ID. But the whole CryptoKitties as a token kind of ecosystem will be part of the NFT parents IDs, if that makes any sense. Okay, so let's actually try to create a child genesis transaction here for the NFT. So let's call our child genesis a block hack child. I'm super creative like that. Child, yeah, let's leave the URI the same. And we're going to create just one additional token because, again, it's NFTs. So what's going to happen is we're going to have to put in the NFT parent ID into this parameter right here. And so this is taking the Genesis ID, popping it down, and then we're going to say NFT child Genesis. So this creates another raw transaction, which we're going to send. And if everything goes correctly, I don't know why it wouldn't, because I tested this earlier. Yeah, so here, NFT1 child. So the block explorer is picking up that this is a child NFT and not a parent NFT. And so here we can see this address has now been assigned with one BGA 2020 child. And the main difference between the other main difference, sorry to interject, the other main difference between the parent NFT tokens and the child NFT tokens is that the parent NFT tokens have the ability to mint additional quantity, whereas the child NFT tokens only have genesis and send. So it just basically locks it in so that these tokens are not going to be duplicated and that a non-fungible token will actually be non-fungible. So here we see the genesis for the tokens right here. And I think if I go here, you can actually see how many was minted, like all the information for that. And let's say we want to create a new mint token, or sorry, a new parent token to mint out an additional SLP child token. So let's say I want to go back here. Let's say I want to create one more the NFT mint, the NFT parent. So I'll mint an additional one. And this pops up. And here we actually have to track the UTXO for where that mint baton is. So once we have that, we could then say send transaction and boom. So minting has been validated on the mainnet. So again, it's tracking, like you have to be very, very careful in where the mint baton is at exactly. Otherwise, like things would just basically not work out. So if you didn't have this V out with the mint baton, it would just be marked as an invalid NFT transaction.
So quick question there. So when you make a copy from the parent, the mint baton passes to the token that you're minting now. And so if you want to create a further one, you have to do it from the newly minted one. You can't do it from the original parent anymore?
Yeah, because so in this step right here, I use the original NFT parent in the NFT child. So that UTXO was already spent.
Okay.
Right. So in the SLP rules, it's tracking like has these UTXOs been spent or not, right? So if it's already been spent and there's a transaction that came in afterwards trying to use the same transaction index, you're basically trying to double spend on the SLP network. So that's why it's like, yeah, that's why it's basically stopping it right there.
Very cool.
Okay, so I minted out an additional parent. There's really no reason to do the send except to just show it off, but because I'm sending it to the same contract address. But just to show that the block explorer will still pick it up as the valid and whatnot. So here's the NFT group send right here. So essentially what this does is imagine if you have a whole bunch of people that want to be creating these NFT tokens, but you don't want them to create an infinite amount of these NFT tokens, right? So what you can do is send the parent NFT token to someone, and that person can use that parent NFT token to then create the Genesis child transaction to create a new child child NFT token. So here we're sending it again to the same address. There's no difference here, but you can send it to other people and it will basically work out kind of similarly. So let me just go back and find where the child Genesis transaction is. So keep in mind, now we have basically two kinds of token IDs here. We have the NFT parent and we have the NFT child. So every single new NFT child that you create will have to be its own token ID, and the parent one will be something separate, right? So here we're taking I already took this, and I plotted in here. We're gonna try to send the NFT child. Again, this is all to the same address. You could change it. I just no, it's just for demo purposes right now. So sending the transaction, crap, I shouldn't have done that. Hopefully I could pull out where that ID is. Yeah, right here. So I guess I was a little bit too fast finger on this. But here we can see the NFT child being created. It is a send transaction, and the amounts are all sent out appropriately. So that basically covers all like the 5 different steps for all of the NFT tokens. And so this is something that you guys could try to play around with as part of your hack if you're trying to tokenize things. And yeah, if anyone has any sort of like questions, now would be a good time to go through them. And in the meantime, I'll just try to set up some conditions where things mess up.
Cool. Yeah, so I might have missed when you clarified. Can you only make one NFT parent at a time, or could you make a copy with like 10, for example? Or is that what you're about to show us?
So I'll try to make one right now, NFT parent genesis. So I've set this to 10 right here. And crap, I keep doing this. So let's just take a look at this transaction that we just broadcasted. Hopefully it'll show up. Yeah. So here is the newly created NFT with a supply of 10, right?
Okay.
So we can be creating that. My code here, unfortunately, is not good enough to pick up like different sets of like if you want to send to like 5, 10, however many people, or if you set the mid baton to a whole bunch of other addresses. So I'll just show real quick what it will kind of look like if you try to like do something inappropriate with the stuff. So
where's the mint baton when you created 10? Do they all get one?
So all 10 is set to the index right here, right? So just like in the regular Bitcoin Cash transactions, you have to do the splitting of the inputs and repiecing for the outputs. So here, because we have 10 and the NFT child only requires 1, let's just try to mint one child NFT. But instead of using just one parents, we're going to use all 10 and just see what happens there, right?
Okay.
So we send the transaction. Again, all of this should be valid. And in fact, this should be a valid SLP transactions as well. It should just have a few burnt. Yeah, it should have a few burnt tokens at this point. Let me just check. So we can see the child genesis created no problem. So we created the 1. It's all good there. But what happened with, or I guess I should probably just view this on the testnet. All right, perfect. All right, so this is the testnet version. Oh crap, I'm dumb. I'm sorry guys, it's not the testnet version I'm looking for, it's the mainnet. Right, so here we see the is this child version? NFT group. Okay, yeah. So you guys can kind of see all this information right here. You can see the child NFTs. That's right there. There should be a burn list actually. Okay, yeah, I won't troubleshoot it live on the spot, but essentially, uh, if you do spend more than one UTXO for the minting baton, you basically just end up wasting it. And I think on the specification page, they'll actually recommend that you split up the UTXOs. Yeah, right here. So they recommend you to split up the UTXOs for the mint, just because it just helps like track which which UTXO is actually valid and available. And so like when you're minting out an NFT token, typically you're minting it out one at a time. So doing it that way, where you're separating the minting baton to different outputs like that, really just helps.
Mm.
Maybe
Cool.
not the minting baton, but the NFT parent. Sorry.
Right. So that could potentially be like something for folks to work on, like ways to like efficiently track where the minting baton is being used if you want to create like a batch of children NFTs in one transaction kind of thing.
Yeah, basically.
Cool.
Basically.
Yeah, this is super fascinating.
All right. Yeah, unfortunately, I probably should have set this up earlier, but the simple ledger has a really good interface for doing all the graphing and stuff. Um, but yeah, it shouldn't be this page right here. Yeah, I won't worry. I won't waste anyone's more time on this. But yeah, that basically just wraps up the presentation right here. Um, Again, last call, I guess, for questions, comments, anything like that. If not, I can be found on the Discord channel under the admin, Lightswarm. So yeah, feel free to ping me a message or just like come online, come up right now.
Okay, I'm gonna unfocus your screencast. Awesome. Yeah, so we'll hang out for a few more moments to see if there's any lingering questions there. I still see some folks hanging out with us. This was a super info-packed session. I learned a crap ton. I knew very little about BCH development to begin with, but it's really fascinating how far, you know, it's come through with the UTXO model, like being able to make contracts and NFTs and all these things that were before kind of said impossible to do using Bitcoin technology. It's awesome how far things have come. So thank you so much, Jerry, for sharing all of this with us. I've done my best to capture all of the links. I probably missed a couple of them there, but they should be in the side panel here for folks that are going through the recording of this. And again, you know, it was super packed, so highly suggest rewatching this. And Jerry's going to be with us throughout the entire hack in the Discord channel. Jerry, if you have a second, do you want to drop your Discord handle just in the chat so it's there for posterity's sake and people know how to find you?
Uh, I'll end the screen share for now.
Yep, I already kicked off your screen share.
Oh, perfect.
Yeah. Cool. Oh, I think okay, there he is. He jumped off the cast and now he's just dropping his thing. Is that your? Yeah, you jumped off the cast, but that's all right. Is that your Twitter handle or is that how to reach you? I think on Discord there's like there's a number after after your thing. It might not be necessary. You might be able to just use Lightswarm. But I think that'll about wrap it up for the evening. Ah, there it is. Yeah, so that's his very specific handle on Discord. So you can find him over there in the in all the chats. And so that wraps up our action-packed workshop session for the day. We are going to be back in another 2 days on Sunday. We got a couple more workshops for you. It's going to be a very exciting weekend, and then we'll be back again on Monday. So on Sunday, what do we got? We got intro to blockchain development, which maybe shifted, but then we also have a how to create an ERC20 token on Sunday. So on that note, I will bid you guys a good evening, good morning, good night, wherever you are in the world. I appreciate you guys for tuning in, and we will see you in the next workshop.